Going to get serious. So we're going to go into some proper serious maths, significantly more difficult than anything you've done before. You will have to work regular on this or you will get completely lost. Yeah, so I'm going to have to explain everything nice and slowly. Well, I won't be able to explain everything. Some stuff's too hard, but let's see. Okay, so let's look at so we're going to do some motivation. So why are we talking about this Laplace? Why, like you sure didn't you solve beam equations last semester? They're all sorted and we've got some more differential equations from chapter 2. Let's see what happens. Okay, so in the previous chapter, so what we do know is the bending moment equation, which says that the second derivative of the bending moment is minus the load per unit length. So that's from last semester. And the deflection equation, which says that the Young's modulus of the beam times the second moment of area times the second derivative of the deflection with respect to distance along the beam is the bending moment. And you can combine both of these to get a fourth order differential equation. EI times the fourth derivative of the deflection is minus the load per unit length. So that's what you've seen before, no problems there. So you can actually solve this using stuff from the last chapter. So that's a bit harder, but we'll look at it, okay? So suppose you have a constant load of 48. So you got EI times the fourth derivative is equal to a constant minus 48. So this is a non-homogeneous linear differential equation. So how do you solve this? So first of all, you solve the homogeneous problem. So that's EI times the fourth derivative is equal to 0. So you solve it equal to 0 first. And we have the auxiliary equation. So you get EI. Now, before you had second derivative, so it was r squared. So this is just r to the 4 equal to 0. Now you can divide both sides by EI and get r to the 4 equal to 0. But what happens here, you have, it's 0 4 times. So this is r equal to 0, but it's repeated. Because r to the 4 has 4 roots, it's 0 repeated 4 times. So if you remember your theory says that a e to the 0x is a solution. To get another one, you need to change it by multiplying it by x. So it's b e to the 0x times x. C e to the 0x times x squared, you have to change it. And then the other one you multiply by x cubed. So this is like what you're familiar with is, say if you get r equal to minus 3 twice, you would say that the homogeneous solution, usually for you it was time. So you'd e to the minus 3t, e to the minus 3t, a plus b, but both of those solutions are the same and your solution is supposed to be two-dimensional, so you change this one by multiplying by t. Now if you can do that here, so that's what we're doing here, we're multiplying by this x to change it. But what happens is on the next one you need a four-dimensional solution because it's a fourth order differential equation, so you end up having to multiply by x squared and x cubed. The next question is, where is the e to the 0x from? Well, e to the 0x is equal to e to the 0 and e to the 0 is 1. So in fact, the homogeneous solution is simply a plus bx plus cx squared plus dx cubed. Okay, the external force in quotation marks is the constant. Now you can't try a trial solution of a constant because it's already in the homogeneous solution. You can't change the constant by multiplying by x because it's still in there. You can't multiply it by x again because it's still in there. You can't multiply it by x again, but it's still in there. But you could take a constant. Now we won't call it e because we've already got an e. We'll call it f times x to the 5. So that's what we're going to trial. So we're going to trial So this is a trial solution, y trial of x is a constant f, and we had to multiply it by x to the 5 to make it very, very different. Now what we want is we want this to solve this, because then our theory says our answer is this plus the trial. So we find its derivatives. So the first derivative of the trial solution is, I'm going to fix the f, and the derivative of x to the 5 is 5x to the 4. Therefore, the second derivative of the trial, I'm going to fix the constant 5f, and the derivative of x to the 4 is 4x cubed. Now I'm going to differentiate it again. The third derivative of the trial is equal to, so fix 5f by 4 is 20f. I'm a bit worried about this. I'm an idiot, aren't I? Because I don't have to go up to x to the 5. I just have to go up to x to the 4. Sorry about that. Let's rub this out as well. Yeah. Sorry, I don't have to go x to the 5. X to the 4 is okay. So this is 4x cubed. So I'm fixing 4f, and the derivative of x cubed is 3x squared. 4f by 3 is 12f. Derivative of x squared is 2x. And one more derivative, the fourth derivative, 1, 2, 3, 4. The trial solution, let's say evaluated at t, is equal to fix the 12f by 2, which is 24f, times the derivative of x is 1. In other words, 24f. So now we're trying to force this trial solution into this differential equation. So EI, so forcing it, we get EI times the fourth derivative, which is 24f, must equal minus 48. And we're looking for big F here. EI are problem parameters. Well, we divide both sides by 24 EI, don't we? So get F is equal to minus 48 divided by 24 EI, and divide above and below by 24, you get minus 2 over EI. So if the constant F is minus 2 EI, it is a solution. So you get a particular solution here, F x to the 4 minus 2 E over EI times x to the 4. So we have a general solution of the differential equation that looks like this. And you can go off and find the four constants A, B, C, D, which would be 4, there'd be multiples of R, A, M, A, C, 1, C, 2, using the four boundary conditions. Off you go. So that's beam equations using chapter 2. Now the problem with this is that if Wx is not nice, now what I mean by that is this external force, minus 48, is nice. What does nice mean? Well, I won't say what it means. It's hard to say what it means. But if it's something like okay, it's continuous anyway. So if you plot it, it's not like if you plot a point load, it's 0, essentially infinite, 0. Or if you plot, similar story, if you plot, say, a UDL, it's 0, suddenly it's equal to 20, suddenly it's equal to 0 again. So that's discontinuous. Whereas all the stuff from chapter 2, the sines, the exponentials, the other things that could be there, they're all continuous. You've no idea what solution to trial. Like say, you see this nice thing, you know what to try. With deltas and that, you've no idea. And then the methods of chapter 2 breaks down. Laplace transforms can handle these problems. Now, those of you now might say, with no problem with the delta functions and the Heaviside functions last semester, why should we learn about a new way of doing beam equations when we already have them? So there's two good reasons. The first is, what if you're interested in a damped harmonic oscillators? That's the stuff from last semester where the external force is a delta function. Now we're going to write that down. So I'll just write down what this would look like. So this would be, you'd have mass times acceleration there, let's just do sum of the, so that's mass times acceleration equals sum of the forces. So the damping is minus lambda times the velocity, which is x dash of t. The spring force is minus kx of t. And suppose in addition there's a kick. So imagine the door and someone gives it a kick. Now a kick here will be modeled by 100. I'm not sure about the units. No, the units are fine. 100 delta t minus 1. So if you have a damped harmonic oscillator with a kick, the methods from chapter 2 will not work. So we need new methods. And another thing might be a damped harmonic oscillator which is being pushed between 2 and 3 seconds. But so someone just pushes it between 2 and 3 seconds, or we may as well write on this one. Mass times acceleration is equal to sum of the forces. So we've got damping force, spring force, and then that force, okay, so it'd be magnitude 200. Well, we know how to turn something. Well, we might remember. So you turn it on at t equal to 2 and turn it off at t equal to 3. So if you want to look at them, the methods of chapter 2 do not work. So the methods of last chapter can't handle that. So it says bad things about the last chapter. Doesn't work very well for us. We want to look at these kind of different things, these discontinuous things. Nothing from last semester is good for this differential equation here, by the way. Why did we do the last chapter at all? Well, one, we wanted to kind of give you something of difficulty before you see something very difficult, maybe to understand what a differential equation is, and also the idea of an ansatz. So that's the idea where you have a rough idea of what the solution looks like and you try and force it. This chapter is a bit more serious. Again, okay, and it can handle these. Now, this particular differential equation that I'm looking at in front of you will be not looked at until level 8. So we're going to be looking at differential equations that you can handle from the previous chapter, but we'll be doing it with these stronger, more powerful methods. The other scenario is probably more interesting to you, is where the load and the beam is not static but dynamic. So the load is changing in time, and therefore the deflection is changing in time as well. Now I'm not even sure is it correct, but it looks something like this. This is possibly level 9 stuff, or level 8, probably level 8. Yeah, level 8. And nothing from last semester can handle this. This is a partial differential equation. Chapter 2 can't handle this. The stuff in this section can. Okay, and to be so powerful, this thing, by the way, the Laplace transform, I would have done a degree in maths and physics, and I never learned about Laplace transform. This is an engineer's thing. It's called the engineer's transform. Mathematically, it's very heavy. So let's get into it. Okay, so some background theory. We need to talk about infinite integrals. Okay, so consider the infinite region S that lies under the curve y equal to 1 over x squared. So this S is this region, and this is the curve y equal to 1 over x squared. Right, now S goes on forever and ever and ever and ever, and you might think its area must be infinite. Now, just to give you, you would have seen a little bit at the end of last semester that just because you add up infinitely many things, it doesn't mean you get something infinite. So another example of this could be, look at this distance. So this is 0 to 2. So if you do jump 1 plus a half plus a quarter plus an eighth plus a 16th plus 1 over 32, you're getting closer and closer to 2. So you have 1 plus a half plus a quarter plus an eighth. You're always jumping half the distance plus 1/16. We would have mentioned this, would have spoken about this last semester. This is equal to 2. So this is Taylor series, which we would have spoken about in Math 7019. So this is a similar story, an infinite area, well, infinite in extent, the length goes to infinity. It's like if you look at it, it ends up looking basically like a line. You might think that this has an infinite area, but let's take a closer look. So let's go up to some point R, which we don't specify. Now, how do you find the area under a curve? You integrate. So we want to integrate from 1 up to R, 1 over x squared. Now, to integrate 1 over x squared, what you should do is rewrite it as x to the power of minus 2. How do you integrate? You anti-differentiate and do top limit minus bottom limit. To anti-differentiate x to the minus 2, you add 1 to the power. That's where your minus 1 is coming in. Divide by the new power. That's divided by the minus 1. And you put in the R and the 1, and you get this area here. 1 minus 1 over R. Now, this number is certainly less than 1, but as R gets bigger and bigger and bigger, goes to infinity, 1 over R goes to 0, and so 1 minus 1 over R gets closer and closer to 1. So what we say is that the area of the region is, find the area from 1 up to R, and then let R go to infinity. So in this case, this area, this infinite area, is actually equal to 1. Because basically in the sense that if you go far enough up, you can get as close to 1 as you want. It never gets bigger than 1. Okay. Right. So here we wrote that the area approaches 1 as x goes to infinity, r/r, really that should be. So we said the area of the infinite region equals 1, and we write that. Yeah, we can write that. So this allows us to define the integral of a function over an interval of an infinite interval as a limit over a finite interval. So we get something like this. Okay, now we're going to write down what the Laplace transform is, and it'll take you a long while to kind of understand what it really is. So what the Laplace transform is, it is a function, but the inputs to it are functions themselves. Okay, so it's a bit tricky. So we're going to use this symbol L for the Laplace transform, and what you're going to put into it is a function of t. I'm going to write functions of t. So this is the set of possible inputs, functions of t. Now, what you can think of functions of t is you can think of these as some kind of a curve. Y is a function of t, something like that. So let's draw one like that. There you go. So this thing is coming in, and then what's coming out is functions of s. Now, what's kind of wacky is that s is actually a complex number, but you can get away. So it's saying, you can get away without knowing that s is actually complex, a complex variable. You can get away just by thinking about the real numbers. So you can put in this number here. Let's say we get out this graph. So we're just going to imagine that s is a real number as such. So you can maybe get out something like that. So see, the yellow thing is what you put in, the orange thing is what you get out. If you were an electronic engineer, this wouldn't be a weird thing for you. You could think of these things as signals. So the first is a signal that goes in and you do some kind of processing, and the orange thing is the signal you get out. Now, unfortunately, we can't really do the intuition on this, because the thing on the left is a function of time, and it could also be a function of distance. But the thing that's coming out is I think it's like a complex frequency. It can't really be understood. It's a mathematical thing. There's a different thing called the Fourier transform that you do at level 8, and it's time and frequency, but this is time and complex frequency, and we can't really explain it in any kind of a way, unfortunately. Now, the way I want you to think about this, because you will have to understand this on some level, even if you don't understand it fully, I want you to think of the time domain as something kind of familiar to you. And the way the analogy I'm going to use is that the time domain is somehow something in English that you understand, and the S domain is something in French that you don't quite well, it doesn't matter if you understand or not. You kind of imagine it that they're different things written there's the same thing written in different languages. So the Laplace transform is like it's more like a translation. But if you take a sentence in English and translate it to French, it's the same thing, it just looks different as such. Now, if you're studying language, you might say that's not quite correct. Now, so you kind of have to understand that. And we'll draw some pictures in the next few pages. The next thing is, can I actually tell you what it is? Well, actually I can. So, right, take a function f of t. So this is t bigger than 0, positive times. So s is some constant, it can actually be a complex number, but we'll just be thinking a real number. If the following integral exists, now not all these integrals exist, but don't worry about that. So 0 to infinity, the function we're looking at, f of t, times e to the minus, change the color up a bit here, s t dt. So we'll do an example of this. So for example, say f of t is equal to 1 over t squared, and s, say, is equal to the number 3 for argument's sake. So you're looking at the infinite integral from 0 to infinity, 1 over t squared, e to the minus 3t dt. Okay, but the thing is that you can put in different numbers. It's not just 3, but loads of different, any kind of number you can put in. If this integral exists, then it's called the Laplace transform of f of t, and we write stuff like this. So we write, there's loads of different things we can write down. So we can write big F of s is equal to that. Okay, we can write the Laplace transform of little f of t is equal to big F of s, and I'm going to write that all in orange now. Or we can write little f of t is sent to big F of s by the Laplace transform. Now what's not really, or you can write maybe little f of t is sent by the Laplace transform to big F of s. But what is not going to be good is writing junk like f of t equals f of s. That's not good. Like a sentence in English and French, it might have the same meaning, but it's not the same thing. I'm gonna kind of, it's the meaning that's the same, but it's a different thing. So this is kind of what we're saying. So the little f of t is your little your yellow thing over here. So you're starting with your yellow thing. This is your f of t. That's your function in, and your function out is your big F of s. And usually, as far as I know, although I better be careful, I think, so when the little yellow thing, the yellow thing will have to probably, actually I better just say nothing there. Yeah, something like this. Okay. So this is what the Laplace transform is. Now calculating this from first principles is difficult. We'll see a few of them here. I think we're going to do some examples, but we'll leave that to a second lecture.